versatile molecules in all of organic chemistry. Yeah, we're talking about alcohols.
But first, let me ask you something. Ever wonder what connects the fuel in your car, the hand sanitizer on your desk, and even some of the most complex life-saving drugs out there?
Well, the answer is this unassuming little functional group right here, the hydroxyl, or the minus OH group. That's what makes a molecule an alcohol. And let me tell you, this little group makes alcohol's chemistry's true MVP, an incredibly flexible building block that chemists use to, well, construct the world all around us. Okay, so here's our game plan. We're going to start by looking at how chemists actually build alcohols. Then we'll see how we can put them to work. After that, we'll get into a real power play called oxidation, and we'll wrap things up with a super fascinating molecular puzzle known as a rearrangement. First up, how do we even make these things? Think of this section as our blueprint for synthesis, where we, the chemists, get to be the molecular architects. So one of the most common places to start is with an alkene, which is just a molecule with a carbon-carbon double bond. But as you're about to see, how you add that OH group, well, that changes everything. It's all about picking the right tool for the job. Now check this out, because this is really cool. What you're seeing here are two totally different results from the exact same starting molecule. Over on the left, we use some acid and water. And look where the OH group goes. It attaches to the most substituted carbon, the one that's already connected to more carbons. That's a classic move. We call it Markovnikov's rule. But on the right, we use a different set of tools, a process called Hydroboration-Oxidation, and boom, the OH group goes to the least substituted carbon. Same starting point, two completely different products. That right there is chemical control in action. Another fantastic way to make alcohols is from carbonyls, molecules with a carbon-oxygen double bond. And again, we've got options. We can use what's called a Grignard reagent. Think of this like a molecular construction crew that comes in and adds a whole new carbon chain. Or we can use a reducing agent, which just adds hydrogen atoms across that double bond, turning it into our alcohol. Two different tools, two very different jobs. But when we start talking about those reducing agents, it gets even more interesting. Because as any chemist will tell you, not all of them are created equal, not by a long shot. Let's look at the two most common ones. You've got sodium borohydride, or NABH4. It's kind of the selective specialist. It's perfect for turning aldehydes and ketones into alcohols, but it won't even look at tougher groups like carboxylic acids. For that job, you need to bring in the powerhouse, lithium aluminum hydride, or LiAlH4. This stuff is a beast. It's so strong it'll reduce pretty much any carbonyl you throw at it. Okay, so we know how to build them. Let's move on and see how this all builds up. Now we're going to put them to work. This section is all about the art of transformation, where our alcohols become the starting point for all sorts of brand new creations. So let's do a little thought experiment. Imagine you're in the lab and you've got 3 unlabeled vials. One is a primary, one is a secondary, and one is a tertiary alcohol. They all just look like clear liquids. So how in the world do you figure out which is which? Easy. You use the Lucas test. Basically, it's a reaction that tries to turn the alcohol into something called an alkyl chloride, which doesn't dissolve, so it makes the solution all cloudy. And here's the kicker. The speed of that reaction tells you everything. A tertiary alcohol, it reacts almost instantly. Poof, cloudy in seconds. A secondary alcohol takes a few minutes, and a primary alcohol, you'll be waiting for hours, if it even reacts at all. It's like a chemical clock that reveals the molecule's true identity. But alcohols aren't just for tests. They're for building things. If you heat up an alcohol with a strong acid, you can actually do the reverse of what we saw earlier. We can kick out the OH group and a nearby hydrogen, and that forms a brand new carbon-carbon double bond. We call this an elimination reaction, and it's a super fundamental way to build bigger, more complex molecules. Okay, now it's time for one of the most important reactions in an alcohol's playbook, oxidation. This is a true power play in chemistry that completely changes the identity and the function of the molecule. So what happens when you oxidize an alcohol depends entirely on its structure. A primary alcohol, which has 2 hydrogens on its main carbon, can be oxidized first to an aldehyde, and then, if you push it, all the way up to a carboxylic acid. A secondary alcohol only has 1 of those hydrogens, so it climbs 1 step and stops at the ketone. And a tertiary alcohol? Well, it has no hydrogens on that central carbon to remove, so nothing happens. It just doesn't react. And this brings us right back to our chemist's toolkit. So the crucial point is that your choice of oxidizing agent is everything. If you want to take a primary alcohol and just climb one rung on that ladder to stop at the aldehyde stage, you use a mild agent, something like PCC. But if you want to go all the way to the top, to get that carboxylic acid, you got to bring out the heavy hitters like potassium permanganate or the Jones reagent. Control, once again, is the name of the game. All right, for our final topic, we're going to venture into one of the most fascinating and kind of weird corners of organic chemistry, the rearrangement puzzle. This is where molecules literally decide to just rebuild themselves. Just take a look at this transformation. On the left, you've got a molecule with two alcohol groups right next to each other, and on the right, you have a ketone. Now, the incredible part isn't just that the functional group changed, it's that the entire carbon skeleton has been rebuilt. The molecule has literally broken itself apart just to put itself back together in a more stable structure. This absolutely amazing process is called the Pinnacle rearrangement. And this brilliantly illustrates how it all goes down. So first, an acid helps one of those OH groups to just pack up and leave as a water molecule. This leaves behind a really unstable positively charged carbon, which we call a carbocation. And here, right here, is the magic step. A neighboring group, in this case a methyl group, literally just hops over to that positive carbon. Finally, the molecule loses a proton, and you get your final superstable ketone product. It's just wild. Now, this might look like total chaos, but it is anything but. Every single step, especially that little hop over we call a 1-2 shift, is a calculated move. The molecule is always, always looking for a lower energy state, and this whole rearrangement is its path to achieving greater stability. It's a fundamental principle that honestly drives so much of chemistry. So after that whirlwind tour through the life of an alcohol, let's just take a second and wrap up with the key takeaways. The big idea is really this. Alcohols are absolutely central players in organic chemistry. We can build them with incredible precision by picking specific reagents to get specific outcomes, and then we can transform them into a whole new cast of molecules through reactions like oxidation and elimination. The real power is just knowing the rules and then choosing the right tool for the job. Which, of course, leaves us with one final question. Now that you've had a little glimpse into the chemist's playbook for making and breaking these amazing molecules, what would you build? Thanks for watching.